Pluto made them come all along. Pluto's circle crosses that of every other planet. Pluto, the baffling little planet at the outside scopes of our nearby planetary group, is running up further in the arena of space technology. Ongoing reviews suggest a reachable experience with Neptune, raising issues among researchers and space enthusiasts. Distinguished figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the results of this astronomical event. However, how did Pluto end up on a crash course with its adjoining planet, and what could this heavenly struggle imply for life on Earth? Join us as we unwind how something massive just crashed into Neptune and how researchers have been left confused by this great irregularity. Pluto, once hailed as an undeniable planet, went through a change in its status, being renamed as a dwarf planet because of its splendid orbit. Regardless of this downgrade, Pluto still charms and interests the galactic community. Later expectations from reputable researchers like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's trajectory, potentially meeting with Neptune, indicating an approaching string of crashes among the heavenly bodies which can have significant repercussions for Earth. Pluto's journey across the Sun stands out due to its unique attributes within our planetary organization. Its orbit is surprisingly prolonged, crossing a lovely 248 years. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun. Adding to its peculiarity is the especially stretched state of its orbit, a flight from the more round paths followed by the primary planets. Besides, Pluto's orbit veers off by 17 degrees from the ecliptic plane, giving its way a more extreme grade compared to other planets. The combination of Pluto's nature and its curved orbit presents layers of complexity to its orbital pattern. One significant point is its occasional convergence with Neptune's orbit. For about 20 years during each cycle, Pluto ventures closer to the Sun than Neptune, opposing expectations based on their separate positions within the nearby planetary group. Diving further into Pluto's orbit, it's fascinating to note that it is not a perfect circle but rather an elongated ellipse, similar to more of an oval shape. This unique orbit results in significant variations in Pluto's distance from the Sun during its journey. At its closest approach, Pluto goes within around 30 astronomical units, AU, of the Sun, while at its farthest point, it reaches more than 49 Australian dollars away, 2 times the distance of Neptune from the Sun. Moreover, Pluto's orbit is inclined at a significant angle relative to the orbits of the major planets in our planetary group. This inclination not only adds to the complexity of its orbit but also plays a significant role in its interactions with other heavenly bodies, particularly Neptune. When Pluto encounters Neptune, their gravitational pulls affect each other, changing their trajectories over time. The complex dance between Pluto and Neptune highlights the dynamic nature of our nearby planetary group. While Pluto was once considered as a solitary drifter in the outer reaches, its near encounters with Neptune underscore the interconnectedness of celestial bodies, each exerting gravitational forces that shape the paths of others. In recent years, upgrades in observational technology have allowed astronomers to track Pluto's movements with remarkable accuracy. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer planetary group. Although the chance of a direct collision between Pluto and Neptune remains low, the possibility cannot be altogether dismissed, prompting continued monitoring and study by the astronomical community. Despite its modest size and remote location, Pluto continues to command attention and interest among scientists and enthusiasts alike. The question arises, why hasn't there been a collision between Pluto and Neptune? The answer lies within the gravitational pull from other planets. Astronomers began analyzing Pluto's path soon after its discovery, and its trajectory puzzled them. Unlike most planets that stick near the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery deepened once they realized Pluto's path crosses Neptune. Despite these complexities, Pluto's orbit remains stable, demonstrating the intricate mechanics of space. Understanding Pluto's orbit is crucial, especially when considering if it could collide with Neptune in the future. This knowledge helps us understand better how our entire solar system works. Pluto's orbit teaches us that even circles that appear risky can balance because of gravity and how things move in space. Continuing to study and analyze these subjects is essential for expanding our knowledge of the universe and our place within it. When we explore space, we discover that things can be odd, and Pluto's orbit is a great example of that eccentricism. Pluto's orbit isn't like those of other planets. It's more oval-shaped, meaning it's not a perfect circle. Sometimes it even gets closer to the Sun than Neptune does. This can make things interesting because Neptune is also moving along its course. There is a small chance that Pluto and Neptune could collide with each other. But no matter its uncommon orbit, Pluto manages to avoid Neptune most of the time. This is because of something called gravitational forces. Gravity is like an invisible force that pulls things closer to each other. So, even though Pluto and Neptune may seem like they are on a collision course, their orbits are carefully choreographed moves guided by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first look can be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the complicated mechanics of our planetary system. This ongoing observation and analysis are critical for expanding our understanding of the universe and our place within it. Imagine if Pluto and Neptune collided. It would be an astronomical event, sending shock waves through our understanding of the nearby planetary group. While we have made progress in understanding space, modern events show that we still have a long way to go. Focusing on what huge planets mean for Pluto's direction gives us valuable clues about how our entire nearby planetary group works. It shows us that where each planet is and how it moves can change the paths of other things in space. Although space is complex, some top scientists are concerned that Pluto could collide with Neptune. This makes them wonder why this could happen, even though it seems unlikely. Neil deGrasse Tyson, a renowned space scientist, has some interesting thoughts about Pluto. He believes that renaming Pluto as a dwarf planet, not a big one like Earth, is a step forward. He thinks we are always learning new things about how things move in space. Tyson sees Pluto's unusual direction as a signal that there's still much we don't know. He believes that the mysteries of space are so exciting. He also knows that big events in space, like Pluto's renaming, get people involved in astronomy. Tyson wants to help people understand the cool and sometimes bizarre things about how space functions. He thinks it's important to talk about how space mechanics can amaze us. Tyson works with other scientists to warn people about the potential risks of Pluto's orbit. In the wake of focusing on Pluto, the fact that it could collide with Neptune at some point makes him concerned. He says this could cause significant problems for our entire planetary group. An accident between Pluto and Neptune could be an exciting and serious event. If it could release a lot of energy and could break apart Pluto, pieces from the collision could fly around space and hit other planets and moons. Neptune may also feel the impact and change the way it moves. Renowned theoretical physicist Michio Kaku, known for his contributions to string theory and science communication, offers an interesting perspective on space exploration. He firmly believes that understanding the future of space travel and the relationship between celestial mechanics and theoretical physics can be gleaned from studying peculiarities like Pluto's orbit. Kaku considers Pluto's orbit to be a window into the future of space exploration. By grasping the complex gravitational relationships and orbital dynamics of celestial bodies like Pluto, we can improve future space missions, assisting with safer navigation through the solar system, predicting potential risks, and planning missions to remote corners of our vast neighborhood. Kaku stresses that patterns gleaned from Pluto's orbit can be applied to exploring other heavenly bodies, providing a roadmap for deciphering remote worlds. He frequently highlights the deep connection between celestial mechanics and theoretical physics, emphasizing that the movements and interactions of planets, including the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, specifically string theory, aims to unravel these principles at their core. He suggests that focusing on the complexities of celestial mechanics, like Pluto's orbit, can provide insights into the fundamental laws of the universe. Like Tyson, Kaku has also contemplated the potential collision of heavenly bodies, referring to it in his theories about the universe. A crash between Pluto and Neptune, while significant in astronomy, could provide a unique observational opportunity, potentially contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to explain the fundamental forces and matter in the universe. Such a collision could create extreme conditions of energy and gravity, shedding light on the behavior of fundamental particles and forces under extreme conditions. Moreover, the gravitational waves produced by such an impact could provide valuable information for testing predictions of string theory regarding gravity and spacetime. While the direct impact on Earth would be insignificant due to our distance from the outer planetary group, the scientific implications could be profound. Understanding events like this could increase our appreciation of the fundamental nature of the universe as described by string theory and other theoretical physics areas. Pluto's unique traits, inspired by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. Yet, the universe holds many secrets, and the three-body problem is just one of them. Scientists anticipate other potential calamities, highlighting the ongoing quest for knowledge and exploration in the vast universe. Although it's highly unlikely, there's still a small chance of planets encountering each other in space. This could happen because planets' paths are influenced by various factors like gravity from other planets, which scientists call the three-body problem. In places like the TRAPPIST-1 system, where there are 7 Earth-sized planets, the gravitational forces create a kind of dance in how the planets move called orbital resonances. Over time, these resonances can make a planet's path less stable and could lead to collisions. Though systems like TRAPPIST-1 are teeming with planets, collisions aren't happening right now. Scientists keep a watch on these systems to understand how planets affect each other's paths, especially when they get close. This helps us understand how planets move in space. Sometimes, there are rogue planets that don't orbit a star and drift around erratically. These planets may have been part of a star system but got ejected due to things like gravity or when another star came too close. Over time, these wandering planets can go far and might run into other star systems. But since space is often empty, the chance of them hitting another planet is very low. Rogue planets are rare compared to the number of stars and planets with stable orbits, so collisions are even more unlikely. When galaxies merge, it can disrupt the orbits of the star systems within them. Although planets probably won't crash into each other directly during these massive events, gravitational interactions can change how stars and planets move. Sometimes, planets get flung out into space, becoming rogue worlds. Other times, they may collide with each other or their host stars. These disruptions can also create new celestial bodies or form new stars. The late heavy bombardment hypothesis suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This bombardment is believed to have occurred because the outer planets, like Jupiter and Saturn, were moving around a lot, which disturbed the paths of many smaller objects in space. As a result, these smaller objects got thrown onto eccentric paths, many ending up in the inner part of our solar system. This caused a massive increase in collisions on planets like Earth. While these impacts didn't involve planets colliding directly, they demonstrated the fact that gravity could make significant changes to how things move in space. This bombardment shaped the surfaces and histories of planets in our solar system. It may have even brought water and organic material to Earth, helping shape our planet.